So we were discussing the load increments that are going to come on the consolidation test on the soil sample. So first of all, the first load increment is 0.25 TSF, the one here, and that stays there for 24 hours or when the reading becomes constant. So after 0.25 we'll apply this load 0.5, and then that stays there for 24 hours, and then either we wait for 24 hours or either we have to look for the constant readings of deformation dial gauge. So any one of that thing happens first, so we change the load increment. And then after 0.5 we go for 1 TSF, that again stays there for a particular time, and then 2, 4, 8 and 16. So after this loading process we also have to do an load and unload process. So that means after reaching the 16 TSF, that load will do its consolidation, and then once it's finished, then we start to unload the sample. Why we need to do that? Because we want to see that if there is any kind of swelling or rebound in the soil specimen. Generally the unloading is done in a fashion that first we have loaded the specimen to 16 TSF, then we load it to 4 and then we unload it to 4 TSF, and then again that stays there for a certain while, then we note the reading, and then after 4 we unload it to 1, that stays there for a certain time, and then we note the readings. So this is how the consolidation test is performed. So so after this the whole process is done, then we will go for calculations. And one thing more before we move to the calculations is that for each load reading, please remember that we have to do this set of reading that we note down, that is time versus deformation dial gauge. So once the 0.25 TSF load comes, this reading set would be there, and then for 0.5 we again will have this reading set, the time and deformation dial gauge, and blah blah blah, yada yada yada. So similarly we will have almost, if we have 1 2 3 4 5 6 7 8 load increments, then we will have 8 such data of loading and 4 or 5 data, similar data for unloading, depending on the increments that we are using for unloading. Now we look at the calculations process. So this is one particular sample that is done with the consolidation test. So we will go through it. So first of all we write sample number here, let's say it was 43, but it depends obviously on your site that you're working. Then we also highlight its borehole location, and then UDS means undisturbed sample, and the depth at which this specimen was obtained. This is diameter of the consolidation ring, 50 millimeter. So this is the internal diameter, that means this is the diameter of the soil specimen also. So why we need that? Because we need to find out the area from it. So we know that pi by 4d square will give us the area of the soil specimen. So and then height of consolidation ring. So if this is the diagram, so this is the h, that is 19 millimeter. So why we need to note the initial dial gauge reading? Because we know that once we are applying load on the specimen, so definitely after each load increment there would be reduction in the height. So we call that, let's say, as h dash. So if 19 was h, that was initial reading, and then we look for the h dash. So this is how it would work. Okay, so so look at the set of the reading. So we have written loading here. So this says in kgs. So we will convert, but you just saw that we were putting up load in case of TSF as a pressure. So how we'll find out the pressure? This kg divided by the area of the soil specimen that we obtain from here. So this will give us the stress test is equal to P over A, and P, this is P, this is 0, and here P would be 0.5, and then 1 2 4 8. So this divided by the area of the specimen will give us the stress, the same stresses that we have just discussed in our last slide. Alright, so that means if we talk about the first load increment, let's say that is 0.5 kg per the areas of the consolidation ring. So at 0 hour, sorry, it should be 0 minute actually. So at 0 minute the reading was 970. This is the, and these all readings, these are the readings of the deformation dial gauge reading. So So simply because time is common, the reading noting of the reading time is constant, so that's why we have just made one column, and for each load we have just written the reading of the deformation dial gauge. So, and this is for unloading, reading of the deformation dial gauge reading. So I think hopefully it is understandable to you. So this is the set that you will note during performance of the test. And once again, first write the initial data, that what was the diameter of the specimen, what was the borehole number, what was the sample number. So details like this we will note. So and then we note the readings. All right, all these readings, and I know it's a laborious work. So after this, and also added to it, we also need to note the weight of the ring plus weight of the soil, and then weight of the empty ring. So in this way we can find out the weight of the wet soil. And at the end of the test, once your test, all the loading and unloading has been done, you will take out the soil specimen along with the ring and put it in the oven for moisture content determination, and then we will find out the natural moisture content. Before we do the this oven drying thing, we also have to note the moisture content, weight of the ring plus wet soil for sample after all the loading and unloading procedure is done. So after noting it, then we note this dry load, and from that we can find out the moisture content of the soil specimen. So after this initial data has been done, then we go for the calculation work. So for calculation work, you see these are the same things that we have obtained from the previous chart. Moisture content, moisture on the specimen, density can be calculated from weight per unit volume, ring diameter, ring height. So from there we can say, and GS, you will be told that what is GS of the soil specimen. Void ratio, you can calculate from that. How you can calculate void ratio is equal to WGS over S, and because our sample is saturated, so this becomes 1. So simply multiply moisture content with the GS value, so that will give us E0 of the soil specimen. Alright, so if you don't want to use the 100% saturation, you can also assume the value, or you can calculate the saturation and use that value. Okay, so these are the initial set of reading and then final set of reading, and then this is the load increment that we applied. This is the major load increment that we applied, and then it has been converted to pressures. These readings are in kPas, that is Newton per millimeter squares. So this set of reading, all right, this is loading up till here and then unloading in this section. So, and then the deformation dial gauge readings for each test. So you see here, these are the values of the deformation dial gauge reading at the start of the test and at the end of the test. So we note these readings, and so we'll find out the change in height, and from there we can find out strain, and lastly from strain you can find out the void ratio. So at the end of the test, the data that we need from this calculations is this, actually this column, that is pressure, and then this last column, that is the void ratio. So we will use these columns of pressure and void ratio to find out the required data. Now what is the required data that we need to obtain from the test? So you see here, I told you that we need void ratio and pressure readings. So this is what we are going to use. That on x-axis you see here we have pressures in kPa, and on y-axis we have void ratio. As I told you already that we need these two values. So for this section is loading and this is unloading. So we will plot a chart, and you see the shape of the chart is almost linear, as we saw the assumption of the Terzaghi's theorem. All right, so this is loading and then this is the unloading section. So we will plot this chart. So it is important to note here that this scale on the pressure is in log scale. You see each increment is 10 times the previous one, so this is a log scale. All right, and we call that as E versus log P curve. So E log P curve is very important whenever you're dealing with soil and you're working in field of geotechnical engineering. So this is the basic test that everyone will assume that you understand this test, and you will hear people talking a lot about the E log P curve, that what is the data, what are the values. So what data do we get out of this test? So we will get out the CC value, alright, that is load deformation curve. That how we obtain it? From load deformation curve. And then we will, from the time deformation curve, we will obtain CV value, and from coefficient of permeability we also get this from the consolidation data. And now what are these things? So we look here. CC is called as the compression index. All right, just a minute. Okay, CC is compression index, and then MV is coefficient of volume change, CV is coefficient of consolidation, and AV is coefficient of compressibility. So these are 4 things that we actually obtain from the consolidation test. Once again, CC is compression index, MV is coefficient of volume change, CV is coefficient of consolidation, and AV is coefficient of compressibility. So you need to know how to find out these values from the graphs of the consolidation test, all right, and the readings of the consolidation test, because we will be using the equations and formulas in our numericals. All right, so we just saw the chart of E log P curve. So this is actually one more. So you see, these are the same data plotted. The only difference is that here the axis, on the x-axis we have a log scale, and here on x-axis we have the arithmetic scale. All right, and you see the difference of the shape. Now why we need to plot these two different things? Because from the slope that is closest to the straight portion, the slope of this straight portion is the AV value, all right, and the slope of this E log P plot, so this is E log P chart and this is EP chart. So the slope of EP chart will give us AV, and the slope of E log P chart will give us CC. All right, so so simply if I write the formula of AV from this chart, so it would be slope of this curve, so that means it will be equal to delta E over delta P. That means I just need to find out 2 values of E and find out the corresponding values of P. Okay, so this will give me, so this would be E2 minus E1 over P2 minus P1. So this is P2, this is P1, and this is E2, and this is E1. So we subtract the values, it will give us AV. Similarly in this chart, again we need to find out the void ratio here, E1, we need to find out void ratio here, that is E2, and correspondingly find out the value of P2 and P1. So but here the chart would be CC would be equal to delta E over log P2 minus log P1, or delta E over log P2 over P1, where delta E is E1 minus E2. All right, so from this chart directly we will obtain the values AV and CC. And now from this equation MV, okay, we can find this from by putting the value of AV will obtain from EP chart. E naught we have already obtained with the start of the test, and MV would be obtained by this formula. And lastly we can find out the permeability of the soil specimen by finding out the value of CV and MV gamma W. So MV would come from here, gamma W is standard, it will depend on the units that we are using, that is 6.24 pounds per foot cube. Only thing unknown is CV. So if we know CV, then we can find out the value of coefficient of permeability, that is K. Now how to find out CV? So to find out CV, we have to use the deformation dial gauge reading versus time chart. So the charts that we saw above, all right, were the EP curve or the E log P curve, but this deformation dial gauge versus time we have not discussed it yet. Okay, so talking once again about this deformation dial gauge versus time chart. So we discussed that any load increment that stays, so for that particular load increment we note the time as well as the deformation dial gauge reading, and time increments were fixed 0.25, 0.5 and so on, and we write the corresponding reading. So the chart plotted between these two values is called as the deformation dial gauge reading versus time. So on x-axis we have time and on y-axis we have deformation dial gauge. We will stop here regarding this CV, and the slope of this chart should be giving us CV. I will talk about this in a while we will perform some numericals related to it. Okay, all right. So this was about the consolidation test. You see, it's a very interesting test and it's very important test. A lot of factors and lot of characteristics of soil can come out from this one single test. So now we talk about theory of consolidation. All right, so it is generally consolidation is represented by U and the units are generally in percentage. All right, so this is EP curve. Okay, all right, and according to the Terzaghis theory, he says that the relationship is linear. Okay, so this should be a straight line like this. Okay, so if and one thing more before we talk about this theory of consolidation, one important thing to remember is that if I load my specimen to 1 TSF, right, so what will happen if you remember the springs theory, spring cylinder theory. So under 1 TSF load, what will happen? In the first step, the pore pressure of the soil specimen will increase equal to 1 TSF. All right, and then with time excess water is going to move out until this delta U becomes equal to 0. That means all the pore pressure that was generated due to this additional load of 1 TSF, that all has dissipated. That means all has moved out. All right, so that means now there will not be any volume change in this soil specimen. All right, for example, it has reduced to this height, so it doesn't matter how long this 1 TSF stays there, but once all the excess pore pressure generated has been dissipated, there will not be any further reduction in the volume of the soil specimen. But now what will happen if I increase this load to, let's say, 2 TSF? All right, what will happen? Now delta U will again increase by an increment of 1 TSF because previously it has been pressed under the 1 TSF load. Then this delta U, an addition of 1 TSF, that will increase the pore pressure inside the specimen. Then again this excess pore pressure would start dissipating, and as the water pressure dissipating, there would be volume change and there would be reduction in the volume of the soil specimen. Okay, and that will continue until all this excess pore pressure of 1 TSF has become equal to 0. So you see here that if I put one load, all right, the consolidation will start. Then again another load, then consolidation will start and go, and sediment will happen until all the water has dissipated. So this stage for one particular load, once all the pressure has been dissipated and delta U becomes 0, we say that 100% consolidation has occurred in the soil specimen under a load of, let's say, 1 TSF or whatever load is acting on the soil specimen. So you get the point that initially when the height of the specimen is at a certain value, right, and then we apply a load, delta U increases equal to that load, and then again with time and depending on the permeability of the soil, delta U would start dissipating by moving water out of the loaded area. And while the water is moving out, soil particles are rearranging themselves, all right, and what will happen? They will reduce in volume. This process continues until all the delta U has reached, and we just learned that once delta U has reached, we say that sample has 100% consolidated, and under the same load there will not be any further reduction in the volume. All right, so if this is the initial condition once the sample was not loaded, and this is, let's say, the final volume that was after the loading. So this loading is placed here. So at this point delta U is equal to, let's say, this is the load is equal to P, and the P load sustains here, and now delta U has become 0. So this means 100% consolidation. So at the start, once we were just loaded the soil specimen. So here E naught was the initial void ratio of the soil specimen, and in this time when all the consolidations occurred, we call that as EF. That is the final void ratio once when the specimen has consolidated to 100% of the value. The same thing has been represented in this chart here. This is the initial stage of specimen E naught, alright, sorry, E naught, and then this EF is the final stage of the specimen. So we can say that this is 0% consolidation and this is 100% consolidation. Alright, so along from EP curve we can find out P naught and we can find out PF. So anything in between, that is represented by ET. So let's say our specimen was loaded, and on the event after some time has passed, some water has dissipated, but all the water has not dissipated. So that will mean our consolidation will be between 0 to 100%. All right, and how can we find out that how much consolidation has occurred? So what we will do, we will take out the soil specimen and we will find out the E value of that. That E value is represented by this ET here. All right, we already know E naught and we already know the EF for the soil specimen. So just plug in the value of ET in this equation. So initial void ratio minus the void ratio at the time that you're interested, initial void ratio minus the final void ratio. So once we subtract these values, so this will tell us what is the consolidation percentage of the soil specimen at the time of your reading. All right, so now we come to the value of finding out the CV, all right, that we were talking about a while ago. So this formula here, this will help us find out the CV for the soil specimen. So small t is actually the time in years. All right, and what is this time? So I'll come back to this diagram here again. Okay, we just said that at the time once the sample was just loaded, we call that as E naught, right? And this time is called as T naught because the loading just started. And with time, as time is increasing, all right, so at the end of consolidation, this will be the final time. Okay, so if I'm interested that after how many time 50% of the consolidation would occur, so I want to find out this particular time T here. All right, so I'm interested to know that, okay, once I load my specimen, so after how much time 50% consolidation will occur. All right, so what will I do? I'll come back to this equation. So I'll write T50 here. Okay, and this is what I want to find out. Okay, CV is the value of the soil specimen. It has, every clay has a particular value of CV. Okay, and H square is the height, is actually not the height of the soil specimen. Okay, I'll come to it in a while, but before that we look at this capital T here. This is the time factor. Okay, how can we find out time factor? So this is the equation. All right, okay, for up to 60% consolidation, if 60% consolidation happened, we use this equation, and if more than 60% consolidation is happening, then we use this equation. It is good idea to remember this equation. It will help you a lot in future. Okay, so coming back to this equation, so we can find out capital T from the two equations mentioned here. So this T50 is what we are interested to find out, and CV, this is the property of the soil specimen. I'll tell you how to find out it. And H square. Now H square is the drainage part. So if I draw a soil specimen here, and this is the load applying, so if we have porous stone at the bottom, this means water can move in this direction. And if there is nothing on the top, all right, or let's say there is an impermeable layer on the top that does not allow water to pass through it, then the height of the specimen would be equal to the H value that we are going to use in this equation. On the contrary, if we have a soil specimen, it has porous stone on the top and porous stone on the bottom. So if you see now, water would be able to move in both directions. In the previous example, water could only move in this direction because we have permeable layer on the bottom side only. But in the second example, we have porous stone on the top and the bottom, or we can say the permeable layers are present on top and bottom, so water can move up and water can move down. In this case, the half the height, let's say if it is h, half of the height would be equal to the drainage path. So h is actually the drainage path. If we have permeable layer only in one direction, then the height of specimen would be equal to h, and if we have permeable layer on both sides of the specimen, all right, in the on top and bottom, then half of the height of the specimen would be equal to the h value, that is the drainage value, to put in this equation. Now lastly, how to find out CV, determination of CV from consolidation test. So as I told you before, that we will need to plot the graph between the deformation dial gauge reading versus time. Now there are two methods. The first method is called as the log time method. All right, in this what we will do, okay, before we talk about so for instance, let's say we are taking, let's say, 2 TSF readings. So under 2 TSF we had time and we had deformation dial gauge reading. So we know that we 0, 1, 2, 4, 8 and 15 minutes, and according to it we find out the values of deformation dial gauge while we were performing the test. Now we plot the same data here. Now on x-axis we have time, that is in log scale, all right, and on y-axis we have the deformation dial gauge reading. So once we plotted the values, so let's say sorry, so this was the graph that was achieved. Sorry about my line. All right, so this curve here is the value that we achieved. Now how to obtain data from it, how to find out CV from it, is that you see there, we will make a line, all right, that is equal to the central portion of the curve. All right, we draw a line here, this one, this dotted line here, central portion of the curve, and then we draw a line tangent to the last portion of the curve. So once again, draw a tangent to the central straight portion of the curve, all right, and then draw a tangent to the last portion of the curve. Where these two intersect, we say that that is equal to 100% consolidation. All right, so this value of t would be 100%. all right, and now if you look at the top portion here, all right, what we will do, we will take any reading. Okay, so let's say this chart was sometime here, so I will take any reading. Let's say I will note the reading of at time of 1 minute. So if this is reading of time 1 minute, then I will note a second reading that is 4 times larger than this reading. So this should be actually 4-minute reading, right? So take any reading, it can be 2 minutes, it can be 3 minutes, or it can be 0.25 minutes, but it's your choice. But from the initial portion of the curve, take a reading. All right, so I took 1 minute, so the next reading should be 4 times the previous one. So let's say this was 4 minutes. What you will do, after taking the readings, find out this horizontal distance between them, then keeping the same distance, find out at the top another line, draw this line here. So this line is equal to R0, and we say that this is equal to 0% consolidation. All right, so now we can take a scale, half of this length would be 50% consolidation, and similarly we can find out places where 40, 60 and 80 consolidation can be find out. All right, so now how to find CV from there? So first of all, I will find out the capital factor T for capital T 50. So I will use the equation here. I will use this equation, all right, because it is less than 50% is less than 60. So I will plug 50 here, 50 divided by 100 square pi over 4. So this will give me T. So T50 would come from this equation here. All right, now h square. Now because we are doing a consolidation test, and if you remember from the figure, we had porous stone on the top and on the bottom, and if you remember, the height of the sample was 19 millimeters. So because it has having drainage in both directions, so h or drainage path would be 19 divided by 2. So I'll plug that value here, square that value, and T50, this is the time for 50% consolidation. So I will this is the mark of 50% consolidation. I'll move straight down, sorry, it should be a straight line, and then move vertically down. All right, so this value would be T50. So put that value from here, plug in all the values, and we will find out CV of the soil specimen that we are testing. So this was the one method to find out CV. There's another method to find out CV. We call that as Taylor's square root method. The procedure is almost the same. On y-axis we have the deformation dial gauge reading. On x-axis we will note the under root of the time. The same table that you used in previous graph can be used here. Alright, the only difference is there that previously we used log value, here we are using the under root values. So on x-axis draw the under root values. Alright, so this pink color here, so this is indicating the chart that we obtained after plotting the graph. Alright, so so what we are going to do is this, that where we will again use this equation. Alright, so according to this equation, draw a line that is parallel to the straight portion of the curve. You see here this blue line that is almost parallel to the central straight portion of the curve. Alright, draw that line. Alright, then what we will do, we will draw another line. Okay, actually this graph is little faulty. There is one error here, let me check that for you. Alright, so actually I'll repeat the procedure. Going back, sorry. So sorry, coming back to my chart. So I simply drew the value of reading of deformation dial gauge reading along with the under root of t. Draw a straight line to the central portion of the curve like this one here. Alright, now wherever this hits the x-axis, so we will note that distance as x. Okay, you see here this is the point where it is hitting the x-axis. Now take another point that is 1.15x. Alright, and mark that point here. Okay, now what we will do, we will draw a line that should be, sorry, I will draw a line that is starting from initial reading, the line where it was hitting the curve, that is R0. Alright, and that is passing this point. So I'll use the scale here. Just a minute, I'll use the scale here. So I'll mark a line, okay, like this. So now this is starting from R0 and this is ending at 1.15x. Okay, alright, so now supposedly where the curve is hitting the, okay, where the curve is hitting the second line, so that value should be equal to the 90% consolidation. Sorry about my graph, that has been little bit misplaced because of this. There was some error in going in my tablet. So this is actually, this is supposed to be 90%. So this R0 value initially, so this is 0%. So this reading is 0 to this whole is 9. So we can divide this into increments. Alright, to find out 20%, 40%, 60%. Alright, so as we are sure about the 90% consolidation, so we can use T90 value here. T90 would come from the equation we have previously discussed, small t90, that is actual time. So this straight value, when I go down, so this would be under root T90. So from there I can find out T90, right? Plug in the values, h square would be again 19 divided by 2 because it's the same consolidation specimen. So this is the second method of finding out CV. So I'll just to make it more clear, you don't get confused, I'll try to draw it again in a quicker way. Just a minute here. So so I'll use this darker color pen so that is more visible to you guys. So on y-axis we have deformation dial gauge reading, on x-axis we have under root of t. So if I plot the chart, it should be plotting something like this. So make a line that is, make a line that is almost straight to the middle portion of the curve. So I'll plot a line almost like this, okay, and pull it upward, so where it hits the x-axis, so this is 0% consolidation. Now I'll measure this distance, this is x, so I'll find out a new point, 1.15x, so let's say it's hitting here. So now I'll draw a line that is starting from 0% and ending up here. So sorry about my diagram. So all right, so now this is the chart. So now we saw that it is hitting the graph at this point, so this value is supposed to be 90% consolidation, okay. So and if I move vertically downward, okay, so this value here would be under root t 90, because it is all under root values. So from there I can find out t 90 and plug in the values, and then you can find out the CV for your soil specimen, okay. So now we will try to, this was pretty much all for the theory portion. Now we will try to solve numerical, and let me have a look at the numerical where I placed it. Okay, let me get back to again, just a minute. All right. So